Good afternoon, everybody. My name's Andy Stevenson. I'm the chair of the Teesside Committee of the Institute of Mechanical Engineers, and I'm pleased to welcome you to what is now our 7th Tech Talk event. So we have two chartered engineers and members of the IMechE speaking today. We've got Sario from Rosen, is going to give a talk entitled Structural Integrity in Pipelines, Failure is Not an Option. And that's going to be followed by King from Durham University talking about structural health monitoring for detecting cracks in oil pipelines. So as a bit of a reminder, if you haven't joined us before, the event will be recorded and will be available to watch on the IMechE's YouTube channel. The last events that we've had have included topics like subsea cables, canal barges, Flettner rotors, and development of the Sophia offshore wind farm and Teesside net zero projects. So you can go online and catch up on those events. We're going to take a break over August. We're going to start again in September with a talk on the 9th of September titled Minimising the Inspection and NDT Work Scopes During Turnarounds, very much kind of process driven, process centred. We're going to be rolling out a series of professional registration events, starting with one on the 22nd of September. And there'll be further details of that emailed out to members in the North East over the coming weeks. So finally, as a reminder, we're always interested in volunteers for different topics that will be of interest to our members. So if you're interested in giving a short talk at a future event, please get in touch with me via the email address shown on the screen or via the IMechE's Near You website. So thanks for listening. If anyone has any questions they'd like to ask the speakers, if you can submit these via the question panel, and I'll relay them to the speaker at the end of the first talk. So I will hand over to Sario to get underway with the first presentation. Over to you, Sario.
Thanks, Andy. Thanks for the opportunity. Thanks for the IMechE for the opportunity to present today. Good evening, everyone, and thanks for joining this session. So today I'm going to be talking about structural integrity and with a special focus on pipelines. The contents of this presentation, I'm going to talk a bit about Rosen to give you an overview of the company. Then I'm going to move to pipeline fundamentals, and then structural integrity in general and some elements like inspection, damage mechanisms and inspection again, integrity assessment, repair methods, and then a conclusion, okay? Right, so very quickly about Rosen. Rosen is a company that is around for 40 years. It started at the founder's home, who started the company by himself, and today is a big company with almost 3,000 employees. It's based in, the headquarters are in Germany. As you can see in this slide, Rosen has a presence in many places around the world, mainly on those hub cities for oil and gas. And we provide pipeline inspection services for about 120 countries. Now a bit about Rosen UK. Since this is a presentation for the Northeast, some of you might have heard about McCall Engineering. McCall is a traditional engineering and consultancy company that was founded in 1996. And McCall actually is an acronym that means materials and corrosion and welding. So these are the areas of expertise of the company. And in 2006, it started to do a lot of joint projects with Rosen, especially in the post-inspection work, which is the evaluation, the analysis, and interpretation of the I-line inspection results. And this partnership worked very well to the point that in January 2017, McCall became part of Rosen, and now all the services that we provided are under the Rosen brand. Okay. Some numbers about the integrity side of Rosen, because Rosen is very famous for the I-line inspection work, for the integrity. Maybe not everyone is aware of it, but we have also a big presence in this in this activity. So we have more than 500 integrity studies completed every year. We have 350 customers around in 65 countries. Globally, we have 200 integrity engineers and 20 principal engineers. So quite a big team of specialists in different disciplines related to pipeline integrity and integrity in general. Okay. Uh, just some idea of some other services that we provided, not all of them related necessarily to integrity. Some material testing, stress analysis, flow assurance. We also have a base in Brunswick, which is the test facility, and also an ILI office, which is related to the ILI business in Silverlink. Okay, now let's move on to a bit of pipeline fundamentals, just to try to get everyone on the same page. So the basics of pipelines. Pipelines is the more efficient way to transport liquid, gas, and solid, even solid products. For example, slurry pipelines for iron ore, for example. So you mix the ore with water and you can pump it using pipelines, which is not everyone is familiar with. Uh, those products can be transported over hundreds of kilometers, sometimes even thousands. Uh, in the oil and gas industry, the main purpose of the pipelines is to get the crude oil from the production sites to the refineries, where it is transformed in different finished products. And sometimes in between, you have the terminals that can work as import or export facilities for the crude oil and also for the finished products as well. And another purpose of the pipelines is to transport the finished products from the refineries to the distribution centers. Uh, my focus here is on transmission pipelines, which are usually the ones that cover larger distances, have larger diameters, and operate at higher pressures. So I'm not talking about the smaller pipelines that we have, for example, for city distribution for natural gas that comes to our houses, for example. But some of the principles are still the same. Uh, an important difference between pipelines as compared to other equipment in the oil and gas industry is the fact that the pipelines, they are not confined to an industrial area, so they go beyond and they go over areas that can be sensitive because there might be communities living nearby, and also because there are some environmentally sensitive areas like rivers, forests, and other regions that can be affected if there is an incident, right? In general, pipelines have a very good safety track record as compared to other alternatives to transport hydrocarbons, but unfortunately, accidents still happen. And this is an example of a high-profile accident that happened in 2010 in San Bruno, California. Unfortunately, 8 people were killed, 51 injured, homes were destroyed, and other homes were damaged. It was a natural gas pipeline. There was a rupture that was followed by an explosion and fire. It was caused by some not ideal practices during the relocation of a segment of the pipeline, and there were some issues with the material quality, and as a result, there was a flaw in a well that grew with time by fatigue, and after a long time after this installation, there was this rupture that unfortunately was a very severe accident. Now, I'm going to talk a bit about pipeline fundamentals, just to give an overall idea. It's well, there are a lot of details about pipelines, but I think for considering the most of its length, it's basically the connection of 12-meter carbon steel pipes that are welded together on site. The main for most of those pipes, the design criteria is to make sure the pipe can withstand the internal pressure, and it's basically using the Barlow's formula, of course, with some uh, design factors to ensure safety and to take into consideration what is around the pipeline and the products that are transported. There are a lot of rules regarding it, but the basic assumption is that, and then it's considered that the pipeline is under membrane stress, which is the constant stress along the wall thickness. Those pipelines are buried, which is something important because the first thing is that you don't see them, so they do a good job for you, but you don't have to see them. And the fact that they are buried also gives additional protection. So it's very hard for someone to hit a pipeline because it's buried. But you see later on that it's still not impossible. It might happen. The products are pumped by means of pumps for liquid lines and compressor for gas pipelines. Most of the pipelines they have an external coating, which is the objective is to protect again external corrosion, which is caused by the soil surrounding the pipeline. And as a second barrier for corrosion, that is cathodic protection because after some time, is it expected that the coating might have some flaws, and in order to protect those areas with flaws, there is the cathodic protection to make sure there is no corrosion, at least to minimize them, of course. And around the region where the pipeline is buried, there is a right of way, which is an area that it's associated with the pipeline, and in this area, it's like a buffer for protection and for easy access. So it's not allowed to have constructions over the pipeline, and then you have this well-defined area that sometimes you can even identify, and there is some signalization that shows that there's a pipeline buried there. So it's another important measurement that's part of the design approach for pipelines. Nowadays, most of the pipelines are piggable, which means that you can run ILI tools along them. So we'll come back to that later. So I'm gonna move to structural integrity, the main elements of structural integrity. What is structural integrity? Well, it's basically the ability of the structure to operate according to the parameters it was designed for without any failure. It looks a very straightforward statement. Usually, if the equipment had a good design, a good material selection, and a proper, I cannot see my slide properly right now. Okay, if there was a proper manufacture and construction, that should be a given. There should be no surprises there. But of course, uh, that is not enough in the long run because for some components over time there might be no modification, no damage, and that's fine. But for other equipments, because of the environments where they are, you might have some issues that might modify the equipment, and it's important for the responsible for the equipment to make sure it's still possible to operate under the design conditions. If not, some corrective actions must be taken, or maybe the equipment must be derated, for example, reducing the operating temperature or the operating pressure. And the changes that might happen in a given structure or equipment are caused by damage mechanisms. There are different damage mechanisms, and it depends on the environment the equipment is in. So a metaphor I like to use for structural integrity is like health for us humans. So it's an indication that your body works well, there are no underlying issues, and you can do everything to the best of your ability. But that is translated to an engineering component. So for that reason, structural integrity must be managed because if that is not the case, and that if there is an active damage mechanism, failure can happen. This is a very famous example of the Aloha Airlines flight that part of the fuselage disconnected mid-flight. The pilot managed to land the aircraft. Unfortunately, one stewardess was killed because she was not strapped. She was standing, so she just flew away and unfortunately died. But the other passengers were okay. It was caused basically by due to fatigue damage, and this fatigue damage was also accelerated by a corrosive environment. Right? It's a very interesting case to study. Well, now I'm going to move on to the elements of structural integrity. Uh, the main elements of structural integrity are the damage mechanism that I already described, which is what causes damage and might affect your equipment. Prevention is a very important part because it's a way to take actions that might minimize the damage mechanisms. After that comes inspection, which is a way to make sure that everything is going well. You cannot just hope for the best. You have to always check to see if there's anything going on that might not have been expected in design, for example. Then it comes the assessment. The assessment is where you look at the inspection results and you have to make to identify how serious whatever you find is. So if you have, for example, corrosion with a 50% metal loss, is that a reason for concern? Is it okay? So for that, you need some assessment tools to evaluate the damage caused by some defects, some indication you can find in your equipment. And the last resort is the repair when as a result of the assessment, you realize that something must be done in order to reestablish the full capacity of your equipment. So it's usually a replacement or some reinforcement in your structure or component. And there are different approaches to structural integrity, the level of detail to any one of those elements, and it's mostly driven by risk. So the higher the risk, so the higher, which is a combination of likelihood and consequence of a failure. So the higher it is, the more refined will be your inspection. The intervals will be shorter, and you will use more refined assessments to make sure no failure should happen in your equipment. So I'm going to talk a bit about inspection. In more traditional equipment, especially in the oil and gas environment, the inspection. Sorry, I cannot see the slides very well. It's a process that allows the damage mechanism to be identified and quantified. It's primarily visual and complemented by non-destructive testing. External inspection usually can be done with the equipment in service, but for internal inspection, it's required the equipment to be shut down, cleaned, and the inspectors need to come inside the equipment to look and see if there is any damage. So the images show that it's not an easy job whatsoever. For pipelines, it's a bit different because unfortunately there is no access for external and internal inspection. Well, actually there is access for external inspection, but as you can see, this is not straightforward. If you want to have a look at a small section of a pipeline, you have to make a big hole and get inside and do the inspection. So the traditional approach for inspection of process equipment from in petrochemical units doesn't work for pipelines. So we need something else. But fortunately, we do have something else, which is inline inspection. Inline inspection is a technology which is around for some time. It's the most effective way to inspect pipelines. Is basically an autonomous, fully automatic, non-destructive testing. The tool travels inside the pipeline. It's moved by the transported fluid. There is no disruption for the pipeline operation. Sometimes it's necessary to reduce the flow rate in order to avoid overspeed of the tool, which might compromise the inspection quality. But on most cases, even that is not necessary. The tools can not only detect, but they can also size They can also, I'm sorry, they can also size and they can very accurately locate features along the pipeline. So the previous picture, it was a field verification that was pointed by the ILI2 results because all the data is saved and there is a report that tells the details about the feature that was detected and its location. And as I said, the detection size is very accurate for most type of defects. Some defects are more difficult to size and detect. So each tool covers specific types of features. So the most common are those for metal loss features, geometric features, cracks, and to record the pipeline route. These images are just some snapshots from a video that is available on YouTube that can give you a basic idea of how is a ILI inspection. So you can see the ILI traveling along the pipeline, and this example is specific for the MFL2, where you have a magnetic field that it's uniform along the wall thickness of the pipeline. But if a discontinuity like a corrosion area is detected, there is a leak in the magnetic field, and that is detected by the sensor, and that is the principle of the detection and sizing of corrosion features. So now I'm going to talk a bit about damage mechanism and still a bit about inspection. So the main damage mechanisms are corrosion, erosion, third-party damage, gel hazards, and cracking. So corrosion erosion is by far the most common damage mechanism in pipeline and can occur both internal and externally. The causes, of course, are different. On the internal side, is associated with the product being transported, and on the external side, is associated with the interaction of the metal surface with the soil, if there is a flaw in the coating, and if the cathodic protection is not effective at that specific location. It can cause local or general thinning. The result, the consequence of the corrosion is a reduction in the capacity of the pipeline for loading in terms of pressure, and it can lead in the end to a leak or a failure, depending on the dimensions and the mechanical properties of the pipe. It can be prevented by a control in the product composition, water removal, also using cleaning pigs that basically drag the water away from the pipeline. So, because water is a big contribution, presents a big contribution for internal corrosion, and also the use of corrosion inhibitors can help to avoid internal corrosion. And of course, a well-designed cathodic protection system. This is an example of an ILI result where each dot here is a feature along the pipeline, which is the x-axis. The y-axis shows the clock position around the pipeline circumference. So you can see a concentration of features in the bottom of the line, because being a crude oil pipeline, the water is usually on the bottom because it's heavier than the crude oil, and then there is a concentration of features there. I'm going to have to speed up a bit. Another type of damage mechanism is third-party damage, which is when there is something hits the pipeline and causes a dent. It can also cause a gouge, where there is also some removal of metal, and that gives rise to a different stress state. And because of the pressure fluctuation in the pipeline, that can lead to fatigue and failure. And then there is a specific tool, which is the caliper tool, that can also detect this kind of feature. It can be avoided with signalization, patrolling in the right of way, and even barriers to add another layer of protection to the pipeline. Now, showing gel hazards, which is basically when the soil especially when there's a lot of water from raining, it becomes unstable, and at some point there might be some soil movement, and then you have additional stresses to your pipeline that, if they are sideways, they can cause wrinkles or buckles, and if they are in the axial direction, they can cause a collapse, which is what's being showed on the picture, where the pipeline was basically severed. In order to prevent them, some stabilization structures can be built in sensitive areas, and also some draining systems can avoid the accumulation of water, which causes the instability. Let's move on. Time is running out. Now, regarding cracks, started to become more common. Cracking issues started to become more common in the last 10 years. There are different types of cracks that can be present in the pipeline. Most of them are caused by welding defects, also by environmentally assisted cracking like SCC, stress corrosion cracking, corrosion fatigue, and any crack can potentially grow by fatigue due to pressure fluctuations and pressure cycling in the pipeline operation. So here you can see different types of cracks with different mechanisms and different morphologies. So it's very challenging to address, because in terms of detection, they can be detected, but they cannot be distinguished. So there must be an additional engineering assessment and judgment to deal with those features. I'm going to have to speed up. So basically, now I'm talking about integrity assessment. There is a lot of methods that assist in the interpretation of the different defects or indications that you can find in the pipeline in order to see if they are acceptable or not. They are based on stress analysis, fracture mechanics, and other methodologies to see if the equipment can still withstand the design loadings. So these are some examples of some calculations to evaluate corrosion defects. This is now an example to evaluate fatigue damage in dents. So there is a more simple approach and then a more sophisticated approach where the ILI information from the geometric tool, the caliper tool, can be used to create an FE model and get a more refined stress concentration factor that can then be used to a fatigue study. And all of that can be done without any excavation, which is very interesting. And then for crack assessment, we use the methodologies that are based on fracture mechanics approach, like the failure assessment diagram that is incorporated as a procedure in both API 579 and also BS 7910. And this would be basically the end result of integrity assessment. So in the chart on the left, you can see the black dots. These are the features, and the y-axis is the failure pressure, and the red line is the maximum operating pressure of the pipeline. Usually it's not constant. It changes along the pipeline, especially for liquid pipelines. So the meaning here is that all the features in this particular pipeline have a failure pressure above the maximum operation pressure. So that means that there's no immediate danger. But of course, if the feature you're looking at, it can evolve with time, it can grow. At some point, the failure pressure might decrease and reach the red line. And as a result, it's important to understand how quick this growth can take place to reach the critical value, and then we can establish a schedule of how many of those features need to be verified and repaired over the course of the next year. So that's the usual integrity management approach. I'm going to jump this one. This is basically the integrity service that can be used based on information that comes from specific ILI tools. Well, repair methods. Unfortunately, I'm running out of time, but yeah, we have the replacement, a replacement that keeps the pipeline operating. Yeah, welded sleeve, composites, buffing for removal of cracks, recoating, which is always used, and then like an overall approach where we should look at all the data to have a broader understanding of how your pipeline behaves and to manage the integrity better. So pipelines are very important, are very safe, but they are failure can have serious consequences, and that should be avoided with a proper integrity management approach. Sorry for going over the time. And last, just the Competence Club for Rosen, where you can get more information if you're interested in those topics. Most of the content is available for free. Thank you very much. Sorry for going a bit over the time. And
Actually, thank you for that, Sarah. That was really interesting, really good introduction to pipelines. So if anyone would like to ask a question, please submit them and I'll read them to Asario. While we're waiting for those to come in, Asario, out of interest in the work that you do, what's the split between onshore and offshore pipelines?
yeah, the onshore and offshore pipelines, they have some different construction approaches. My experience is mostly on onshore pipelines, but the offshore pipelines, for example, they are more susceptible to internal corrosion because you basically are working with the raw material, which is the crude oil, which can have a lot of water associated, a lot of salt, a lot of sand. So it's a really nasty environment. On the other hand, the wall thickness for offshore pipelines is usually determined not by the internal pressure, but the loads during the loading operation of the pipeline. So you have a bit of a extra thickness, an extra allowance for corrosion. Um, yeah, I think that would be the main difference. And of course, offshore pipelines would not be susceptible to mechanism like SEC because it's fully wet, so there's no risk of the different chemical interactions that you usually have in a buried pipeline. And of course, the third party damage can happen. For example, an anchor for a ship can hit the pipeline, but I would say it's probably less likely than for an onshore pipeline. But of course, there are many other differences.
You mentioned in the presentation that there was it was becoming more common to find cracks in pipelines. What's the kind of reasoning behind that, do you think?
I think the main reason is because usually when you have a crack that is associated with a weld defect, if the pipeline doesn't have a lot of cycling, it will probably be there forever and it will not grow. It's very much the case for gas pipelines. On the other hand, when you have SEC, it's a time dependent mechanism. So you need time for your coating to degrade, and at some point you have failure in the coating, and then you have this interaction with the soil, and this kind of failures started to happen in North America, and probably because those pipelines operate at higher pressures, and I think that's why it happened there first. But in the last 10 years, we are seeing it happening everywhere, like South America, Europe. That's still not a case in the UK, not so far, and no cases in Africa, but it might be just a matter of time because it's a time dependent mechanism. And of course, it's also associated with the quality of the construction. So if the construction has a better quality, the likelihood of having those failures would be lower.
Okay, I've just got a final question that's come in just about Rosen and the UK office. So do you cover the UK only, or do you undertake studies for the rest of the world?
No, we work for the whole world. Actually, I'm not in Rosen for a long time, but I still have done any work for UK. I'm currently working for South America and also for some projects in Europe and Canada. But it used to be a centralized team that work for the whole world, and of course also for UK customers, clients. But we're starting to have some teams working spread to be closer to the clients and to have a more let's say a more closely presence. But most of the team is here in Newcastle.
Excellent. Okay. Well, thank you very much for your talk, Gustavo. That was really interesting. So thanks for that.
Oh, thank you.
We're going to move on to our second now. So King, if you're ready to pick up, I will let you introduce yourself and your presentation.
Okay. So thanks for Andy. Okay, so good afternoon, everyone. Thanks for the opportunity that provided by iMechanical E. So the title of my talk today is Structural Health Monitoring for Detecting Cracks in Oil Pipelines. At Durham, our research project covers wind turbine blade measurement, battery end-of-life performance evaluation, power quality signal detection and control for urban distribution networks, to name but a few. But today's presentation is much more focusing on structural health monitoring for detecting the cracks in the oil pipeline. So someone might be know the CIDIC, which he said in 1914. He said if a thing exists, it exists in some amount, and if it exists in some amount, it can be measured. So there are 4 date measurement scales: nominal, ordinal, interval, and ratio. So the nominal scale are used for labeling variables without any quantitative value. So example of nominal scales are gender, hair color, and where do you live. A good way to remember all of these is that nominal sounds a lot like name, and nominal scales are kind of like names or labels. Ordinal scale are typically measures of non-numerical concepts like satisfaction, happiness, discomfort, and so on. So the slides showing here, the hot scale and the pain scale, are 2 good examples of these. With ordinal scales, the order of the value is what is important and significant, but the difference between each one is not really known. The other scale, which is interval scales, are numerical scales in which we know both the order and also the exact difference between the values. The classic example of an interval scale is Celsius temperature, because the difference between each value is the same. So for example, the difference between 60 and 50 degrees is a measurable 10 degrees, as is the difference between 80 and 70 degrees. So interval scale are great, but we can't calculate ratios, which brings us to our last measurement scale, which is the ratio scale. Ratio scale tell us about the order. They tell us the exact value between unions, and they also have an absolute zero, which allow for a wide range of both descriptive and also inferential statistics to be applied. A good example of ratio variable include height, weight, and duration. So when we're looking at the measurement techniques, we first look at the data acquisition method. Normally, data acquisition techniques will be classified as non-contact method and tactile method, sometimes also called contact method. The non-contact method depends on the data being acquired. They can also be classified as the optical method, acoustic method, and magnetic method. For the oil pipeline crack detection, we will use both acoustic and magnetic methods for the measurement. So I'm just here talking a little bit about the problems. The oil pipeline leakage is a major environmental concern. Therefore, a safe and reliable pipeline network is vital. Currently, the average age of the oil pipeline in the USA is over 50 years. And due to the various causes, pipeline leakage of more than 110 million US gallon of the crude oil and petroleum products have spilled from the USA mainland pipeline network alone. And also the underwater pipeline leakage could bring even more consequence to the ecosystem. So an early detection of potential pipeline leakage is very important, not only just for the environmental concern, but also will have a big economic benefit. So the figures on the right-hand side is a photo of the Enbridge Line 6B, which ruptured in July 2010 and spilled 24,000 oil-filled barrels of oil into the Kalamazoo River in Michigan. So these are becoming the largest inland oil spill in U.S. history. So talking the situation in the UK, so the UK Onshore Pipeline Operator Association, which is UK OPA, they are the regulators for the UK pipeline product loss. They have published a report in 2018. So the two figures I put in here are from their report. So the left one shows the failure frequency during the period from 1962 to 2016, which 0.212 incidents per 100 kilometer year. So for the last 5 years, for example, 2012 to 2016, which is 0.087 incidents per 100 kilometer year. So in order to see the result over recent period, the moving average for each year is calculated with reference to the incident from the previous 5 years. So for example, 2012 to 2016, 2011 to 2015, or 2010 to 2014, etc. So the figures show on the right-hand side, you can see the development of the product loss incident frequency by cause. Pipeline failure due to causes other than those defined on the graph will be classified. The first one will be the external interference, second one which is corrosion, and third one is material and construction. Fourth one will be the ground movement. These are generally classified as other on the chart, and also these other accounted roughly about 22% of the total failure rate. So from this, we can see that it's important if we can find a good way to do the early detection, which is most importantly, which will be see the environmental benefit and also economically. So when we're talking about method which used for the structural health monitoring, a lot of the peoples will taking a lot of the different measurement. So I listed here a few of the methods which commonly being used in the oil and pipe industry. One of the particular one, which is the ultrasonic, this kind of method which can be used to do as a flow detection, dimensional measurement, and also material categorization. So this method, they are very sensitive to the surface and subsurface discontinuities. They also have the high accuracy and can measure the location, size, and also the shape of the defect. And also they can produce the detailed image for the defect. But also the disadvantage for this type of application is surface must be accessible. So that's depending on the condition of the pipeline where they laid, and also the extensive training which need to master this piece of the techniques. And also difficult to inspect the materials that are rough, irregular, thin, small, or non-homogeneous. So every technique which listed in here, they all have the advantage and also the disadvantage, depending on the applications, location, and also the structure of the pipes which we actually need to detect in the crack with it. So the techniques in question for today's presentation is to using the impedance-based method, which is using a surface-bound piezoelectric PZT transducer patches. So this technique utilizes the piezoelectric property of PZT transducer patch, which they are bounded to a structure acting as both a sensor and also a actuator, to detecting a change in the mechanical impedance of the hot structure when a defect such as a crack is present. So the feature demonstrates the piezoelectric effect on a polarized cylinder of the piezoelectric material, taken as a transducer patch in the case of this project. So from the figure A, which is showing the transducer patch, is the arbitrarily paralyzed positively with the positive charge at the top of the shape and the negative charge at the bottom. So if you see the D and the E, these are presented a compressive stress on the patch. This will produce a negative charge, and a tensile stress will produce a positive charge. So looking at the B and the C, these two figures, which is actually, you can see the negative electric field applied will extend to transducer patch, and the positive electric field applied will contract it. So this is important, as it can be seen that if an AC signal is passed through the transducer patch, it will expand and contract as a current alternative. So it can operate, so it can vibrate. In addition, it will vibrate at a frequency of AC signal being passed through it, as the expansions and also contractions will increase with a fast charging current. So overall, the impedance-based method uses a piezoelectric transducer patch driven by AC current, and they are swept between a range of the frequencies. So for the experimentation configuration in this work, a mild steel pipe was used, which has a length of 1 meter, an outer diameter of 101.64 millimeter, and also a wall thickness of 2 millimeter. So the coordinate system used to indicate the location of the transducer and the holes drilled to simulate the damage described in the figure. So you can see from the figures, we put the 5 patch transducers and also the location of the transducers are also shown in the figure. So you can see that 1, 2, 3, 4, 5 on the different location on the pipe. So the baseline impedance measurement of 5 transducers were made with an undamaged pipe, with a frequency range of 10 kHz and 20 kHz in steps of the 5 kHz. Subsequently, the damage were made to the pipe and impedance measurement within the same frequency range, and frequency steps were made for all 5 transducers. The damage conditions investigated are listed here, where the distance x and also the angle theta of each of the hole drilled are referred to in the coordinating system shown in the previous slides. In order to quantify the damage, a damage matrix RMSD for each damage condition was computed for each transducer. The RMSD damage matrix is the root mean square differences of the damaged impedance from the baseline over the frequency analyzed. So where the REJ1I is the impedance of the PZT measured under health conditions, REZ2I is the impedance for the comparison with the baseline measurement at frequency interval I, and N is the total number of the frequency points used in the comparison. So the figures showing the RMSD value obtained for each transducer for each of the damage conditions. As the RMSD is a measure of the damage, the higher the value, the more severe the damage is. So the damage under condition 1 and condition 2 was a 2 mm diameter hole and a 4 mm diameter hole at x equals to 0 and theta equals to 90. It can be seen that the damage matrix obtained under condition 2 are in general higher than that obtained under the condition 1. Under condition 3, 2 5 mm holes were drilled with one at x equals to 0 mm, theta equals to 90, and one at x equal to 20 mm, theta equal to 90. So it can be seen that the matrix obtained by transducer 1 and 4 under this condition are similar to those obtained under the previous two conditions, while an increase in the matrix can be observed for transducers 2, 3, and 5. Under condition 4, one more 5 mm hole was located at x equals to 20 mm, theta equals to 90, in addition to damage under condition 3. Again, there is no significant increase in matrix observed for transducers 1 and 4, while marked increase can be seen for transducer 2, 3, and 5. Over the years, a number of the researchers have proposed various damage matrix equations to provide better correlation between the matrix and the degree of damage. Primarily, they are variations of the basic statistical model, and the more common ones, which I listed here, which is RMS D1, D2, D3, and D4. Coming to the presenting the results, so the value of these damage matrix were computed from the impedance measurements obtained from all transducers for all the damage conditions. So you can see that's the figure A, B, C, and D, which is showing the RMS D1, RMS D2, RMS D3, and RMS D4, the damage matrix respectively. So they are not that much different, but for the one which the green bar, and that's have the significantly different for all the measurement. So you can see that figure A and B show the RMS D1 and RMS D2 metrics. So the trends shown by the figure A and B are such that there is no difference in the matrix obtained under all conditions for transducer 1 and 4, and the increase in matrix with increase in damage can be observed for transducer 2, 3, and 5. So figure C is showing the RMS D3 matrix, and the figure D shows the RMS D4 matrix. So from the result obtained, it can be concluded that all the damage matrix algorithms show us a similar trend matrix increase with damage. Apart from RMS D3, the results show that the damage matrix are very sensitive to damage. See, for example, condition 1 and 2 with a single 2 mm diameter and 4 mm diameter hole respectively. There is a very strong correlation between all damage matrix and distance of the transducer from the site of the damage. So although the results obtained in the present work have demonstrated that impedance-based method can be used to detect the cracks in the pipelines, so we propose the following we propose the following work, which might be improve the efficiency of the pipe inspection using PZT transducers. First one is to investigate the effect on the damage matrix of the frequency range analyzed. Second one is to correlate the damage matrix with the transducer distance so as to locate the site of the damage. The third one is to adapt the current setup to investigate crack detection using other structural health monitoring method techniques. So I think that is everything for my presentation.
Okay, thank you very much for that. That was interesting. If anyone would like to submit a question, please do so, and we'll pass this on in the last few minutes. If I can ask a question, has this been purely theoretical, or have you undertaken kind of trials in laboratories? Where does the kind of technology sit?
Sorry, can you repeat questions, please?
The work that you've done to date, has that just been theoretical, or have you done experiments within a laboratory or any field trials yet?
So the work which we did, we do have the laboratory test rig, and so we actually use them to testing or validating our method. We currently had some discussion with the BP, and we also have a student project with them in the past. So try to introduce our methods to see whether they would actually take on or making any real field trip, field work on their pipelines.
Yes, to try and to bring the technology on. Okay, that's very interesting. In terms of timescales, how far away do you see the kind of verification of what you're doing being before that could potentially be implemented into the field?
So I think that is depending on the complexity of the situation on the field. And I think currently, it's also depending on the technique which we use. So for the pipeline, you can have the multiple transducers. I think the hard work is actually to reconstruction the image. I think that's more difficult to quantify the crack, the information, the size, and also the depth of it.
Okay, thank you. If we haven't got any other questions, then we'll bring today's Tech Talk to a close. Thank you very much to Asario and King for giving up their time and presenting today. It's always great to hear what other engineers get involved with. Thanks to Emma at the IMechE headquarters for setting it up, and thank you everyone for joining us again. And hopefully we'll meet again in September when we have our next Tech Talk event. Okay, so good evening and thank you.
Thank you. Thank you, everyone.
Thank you.